Jnanam paramam dheyam. Knowledge is supreme.
Let us now see what are the other options which are available with us in case the first principle dynamic model has limitations for the process under consideration. So, in that case we go with what is known as an empirical model. So, empirical model will be a model which will be developed with the help of experiments. So, as we had seen earlier, a dynamic model is that which gives you a relationship between inputs and output as a function of time. So, while generating an empirical model, what is done is that you have a process already built and then you give changes in the inputs, which may be a manipulated input or a disturbance input if possible, and then capture the response of the output as a function of time. So, let us say we have a process. This is manipulated input, this is disturbance input, and this is output. So, we give some change in the input. Let us say we give some step change in the value of input and we try to record what is the value of the output. Let us say because of that change the output did not change for some time and later on started showing some response. So, we have how the input changes as a function of time and we have recorded how the output changes as a function of time, and then we try to find the function which is the process model which will convert this input into the output. So, we do not need to necessarily know what is inside the process, what kind of equipment is there, what physical laws it follows. All we are interested in giving some change in the input and then record the output, and what mathematical function would give me a relationship which says that if a particular input is given to the process, the output which we saw is same as what will be predicted by using this particular model. So, there are multiple ways in which these empirical models can be formulated. One is a simple regression model. We have the input, we have data about how the input changed. So, these are all the values of ui, and then we have the values of all y's which are yi, and we can simply do regression which will tell me yi as a function of ui. So, the simplest way it can be done as a linear regression or a non-linear regression model. The other way we can capture the response is for a step change of a certain magnitude. Let us say this step change was of magnitude 1, that is known as a unit step change. You capture the output at different time instances. So, let us say these are the different time instances, and then you note down for a unit step change in the input what are these coefficients. So, we will call it y0, y1, y2 all the way up to yn. So, listing these coefficients will tell me how the system responds for a unit step change. So, such kind of a model will be where we tabulate the values of y0, y2 up to yn would be known as a step response model. In the early advanced controllers, these type of models were used to capture the response of a process. So, the idea is if there is some input which is given to the process, you can always write it down as a summation of multiple steps, and then assuming the process to be linear, we can just add the responses corresponding to each of the inputs. Let me explain this phenomena again. So, step response model says that if I have a unit step, my output will give me a trajectory of this. These will be the changes from the original steady state. Now, let us say the input was something of this form. So, let us say this was the input given to a process and I want to predict what is the output. So, we can always decompose this particular input sequence as a series of steps. So, let us say the first step is this way, the second step you can say is 0 all the way up to this point, and then some addition so that the total becomes this, and so on. So, by addition of multiple steps, so this can be written as a summation of multiple positive and negative steps. And we already know if a unit step is given, this is the response. So, if some magnitude step is given, the response, so let us say that magnitude was A, then the response will be A times y0, y1 all the way up to yn. And when we have a summation, then the response will be the summation of all the responses for the constituent steps. So, this way assume, so this all is valid assuming a linear process. If you assume that a process is linear, then any input can be written as a summation of multiple positive and negative steps, and then the response can simply be scaled and added together to get the final response. And then lastly, these empirical models can be as complicated as a artificial neural network type model as well. Mostly from control point of view, we would not go to the level of artificial neural networks, but regression models or step response models, those are quite commonly used empirical models for control systems. So, now let us look at what are the advantages and limitations of these empirical models. And the first advantage is straightforward. These were developed as alternatives to the first principle models. So, especially for the cases where first principle dynamic models are difficult to arrive at, these first principle models will be easier to develop. Because in a real plant there may be hundreds of process variables, but out of those maybe few, let us say 5 or 6 are inputs and correspondingly 3-4 are outputs. So, in that case we just need to develop individual pairwise relationships between inputs and outputs, so which may be significantly lower than the total number of equations which you need to write for a first principle model. Now, let us look at what are the limitations. And the major limitation is that these models heavily depend on how these models were arrived at or what kind of changes which were given to the inputs. This is known as excitation of the process. So, in typical control language, what we talk about is how much did we excite the process, that means how much was the step change given to the input, and accordingly the validity of the model is more or less of the same order as the excitation. So, if while developing the empirical model the changes in the inputs were not significant, then when you use the model for prediction, that time the predictive capability is also limited. So, these do not extrapolate very well. But as I said earlier, depending on what is the main requirement, is it just getting the relationship between input and output which captures most of the expected changes in the inputs, then empirical model may be better than theoretical model, especially if the theoretical model is very difficult to get at or the parameters of that model are difficult to get by. And then it takes us to the last type of dynamic model, which is sort of a middle ground between the empirical model, which are known as black box model, and the theoretical models, which are known as white box model. So, these are called as grey box models. So, here what we do is they are actually a combination of white and black box model. So, you use parts of both these methodologies. So, we use some parameters from the first principle model. Typically it is the form of the input output relationship which we get from the fundamental or first principle modeling, and while getting the parameters of the system we use experiments or empirical data. So, in a way it is a combination of the two methodologies, and a very commonly used grey box models from the control point of view is known as a first order plus date time process. So, as we start moving into this course, we will be using this particular type of model. But at this point, let me just tell you what it means. So, it is a first order plus date time model. So, here what we do is we assume a form of a function which is kp e raised to minus TDS over tau s plus 1. So, this model form is assumed, and then when we get the data between input and output, we use this data to find the three model parameters which are Kp, tau and Td. So, the distinction between empirical model and a grey box model: if it was an empirical model, I would have taken all this data and simply fitted either a regression model or a step response model between these two without considering what sort of form that equation would take. In a grey box model, we assume a certain form as well, and this has the form has physical significance. So, it is not a completely mathematical function which captures the relationship between input and output. There is physical insight into developing that sort of model, and then the data is used only to get the parameters of the model. So, in a way it captures advantages of both the theoretical model, white box model as well as the black box model, in a sense that it incorporates process knowledge, therefore it kind of gives you better extrapolation capabilities, and it's also easier to develop than first principle model, because here you are using experimental data to kind of arrive at the parameters which are very difficult to get theoretically. If we want to look at a limitation, it is still an approximation. We are assuming a certain form which may not capture the exact reality of the process, and also we are using mathematical tools to arrive at the best values of these parameters, which may not exactly match the data, but within a certain acceptable range it will give you a fit between the input and output. So, they are still approximation models, and they will have certain validity range across which their predictive capabilities are there valid, but still if you want to compare with the black box model and a grey box model, the grey box model in that case would have much larger or wider applicability than compared to the empirical model. So, in a way it sits nicely as a trade off between the accuracy of the model and the ease of developing the model, and that way many a times a grey box model is preferred over either a theoretical model or a black box model. So, we will take a short break here. Thank you.